So this first set of problems is going to be using Heisenberg's uncertainty principle, which is basically that the product of the uncertainty in the position and momentum is greater than or equal to h bar, or the product of the uncertainty in the time times the energy is greater than or equal to h bar, where h bar is equal to Planck's constant over 2 pi, which comes out to be 1.055 times 10 to the minus 34 joule seconds. All right, so in this problem, we've got a proton that's confined within an atomic nucleus that has a diameter of 4 femtometers, and we want to know the minimum speed of the proton. So what do we know? We know the mass of the proton, 1.67 times 10 to the minus 27 kilograms. We know the diameter in which it's confined is 4.0 femtometers, so that's going to be my delta x. That's the uncertainty of its position. It's somewhere within the 4 femtometers, and a femtometer is 10 to the, didn't leave myself room, 10 to the minus 15 meters. So it's 4 times 10 to the minus 15 meters. I want to find the uncertainty in the speed, so I want to find delta v. Okay, so how do we get it from these equations? Well, P is m times v, so delta P is m times delta v. So I can find that, let me write it out in whole. So delta x times delta v times m is greater than or equal to h bar. So delta v is to be greater than or equal to h bar over delta x and m. So I'm going to put that in. So I get delta v is greater than or equal to h bar 1.055 times 10 to the minus 34. Delta x is 4 times 10 to the minus 15. And m is 1.67 times 10 to the minus 27. I get 1.6 meters per second. Okay, equivalently, you could have solved this by finding delta p is equal to h bar over delta x. So that would have given you, let me just put down the number, 2.3 times 10 to the minus 20 kilogram meters per second, and then found delta v is delta p over m, and you would have got the same answer. Okay, so you can do it either way, do it all in one calculation step like I did, or do it in 2 steps. Okay, let's do another one where we now know the uncertainty in the momentum, and we want to find the uncertainty in the position. So here I'm given the momentum is this 3.2847 plus or minus 0.0025 times 10 to the minus 30. So this plus or minus, that's my uncertainty. Okay, so I want to find delta x is going to be h bar, I guess I should put greater than or equal to h bar over delta p. So it's going to be greater than or equal to 1.055 times 10 to the minus 34 divided by delta p, which is 0.00025 times 10 to the minus 30, and I get 4.2 meters. So that's actually pretty big, right? That's probably about as big as wide as the room that you're sitting in. So that's the minimum uncertainty. You can only locate the electron to within about the size of a room if you know its momentum so accurately. All right, let's do one where we use the other equation, the energy-time equation. So we say if an excited state of an electron is known to have this lifetime, 1 times 10 to the minus 7, so that's my delta t. What's the minimum uncertainty in the energy of the state? Okay, so we know delta E, delta T is greater than or equal to h bar, so delta E, the uncertainty in the energy, can be h bar over delta T. And so again, it's just plug and chug h bar 1.055 times 10 to the minus 34. Delta T, 1.0 times 10 to the minus 7. I get 1.055 times 10 to the minus 27 joules. So that's a pretty small uncertainty in the energy, even if your energy is only electron volts, and electron volt is 10 to the minus 19 joules, right? So it's still very small compared to the energy of an atomic state.